Welcome to Maths with EJD. In this video, we now consider Laplace transform for unit step function, or what you can call the Heaviside function. Okay, so first of all, some general views. The unit step function, also known as the Heaviside function, is an important mathematical function used in engineering, control systems, and signal processing. It is defined as u of t equals, so it is a step function. It is 0 when t is less than 0, and it is 1 when t is greater than or equal to 0. So the unit step function, of course, you can see it's a step function for sure. So this function now, this function effectively activates, let me highlight that it activates or deactivates. It activates or deactivates a signal at t equals 0. So for t less than 0, the function is 0. The function is 0, as we saw up there already. The function is 0 at t less than 0. And for t greater than or equal to 0, it is 1. Okay. Now that is the unit step function, or the Heaviside function. So it's about activation depending on the value of t around 0. So we also then have a shifted step function. So a shifted step function denoted as, so now we have a shift in it. It's denoted as u of t minus a. Previously, the step function is just u of t. Now, the shifted step function is u of t minus a. So we have it shifted sort of backwards, a steps. So here now, it activates, a shifted step function activates, the normal function activates about 0, right? When you get to 0, it switches on, and then then greater than 0, it's on, less than 0, it's off. So a shifted step function denoted as u of t minus a activates at t, it activates at t equals a. When t equals a, that's when it activates, rather than at t equals 0. So in that case, the definition of that, the definition is u of t minus a equals 0 when t is less than a, and it is 1 when t is greater than or equal to a. Okay, so then the unit step function is especially useful in representing piecewise functions. Piecewise functions and systems that start or change behavior. They start or change behavior at a specific time. So, I mean, this reminds me of something like a thermostat, right? So a thermostat regulates temperature. So when it gets to a particular threshold, it either switches off or switches on. So this is a very good example of that. So having talked about this, can we move on to uh okay, let this come here now, and then we have this. Okay, not this now. Let's go green. Okay. Now let's talk about Laplace transform of the unit step function. That's the key deal here. Laplace transform, Laplace transform of the unit step function. So we've seen the function itself. Now let's see its Laplace transform. Okay. So the Laplace transform, as we know already, is powerful. I mean, we keep saying that the Laplace transform is a powerful tool for analyzing functions, especially in systems and signal processing. Okay. The Laplace function, because it's more like a reminder, right? The Laplace transform of a function f of t is defined as the Laplace of f of t, and that is equal to integral from 0 to infinity of e raised to power minus st f of t dt. So this is established. Now, for the unit step function, the Laplace transform is well defined as follows. So first we have Laplace transform of u of t, the normal unit step. So the Laplace transform of u of t, the regular unit step function. Okay, so the Laplace transform of u of t, the unit step function, is L of u of t equals integral from 0 to infinity e raised to power minus st u of t dt. So since u of t is equal to 1 for t greater than or equal to 0, that's known, then we get the L of u of t is equal to integral from 0 to infinity of e raised to power minus st. F of t now is 1, so we just have e raised to power minus st dt, and we just simply have 1 over s, and that is for s greater than 0. So we have this for that part. So this simply means this means the Laplace transform of the unit step function is 1 over s, and it is valid for s greater than 0. So let's talk about the Laplace transform of the shifted step function. Laplace transform of u of t minus a, the shifted step function. So the Laplace transform of a shifted step function u of t minus a, which starts at t equals a, is given by the Laplace of u of t minus a which is equal to integral from 0 to infinity e raised power minus st u of t minus a dt. Okay, so and here we know that for t is greater than or equal to a, u of t minus a is equal to 1. And for t less than a, u of t minus a is equal to 0. So we can rewrite the integral as the Laplace of u of t minus a equals integral from a to infinity of e raised power minus st dt. So in that case, that simply means if we evaluate that integral, we have e raised power minus st all over minus s, and that is evaluated from a to infinity. So of course, as usual, I like to bring out the minus 1 over s. So minus 1 over s into e raised power minus st from a to infinity. So that's minus 1 over s e raised power minus s infinity minus e raised power minus s a. Okay. So this is minus 1 over s into, of course, this is e raised power minus infinity minus e raised power minus sa, like that, or as, and that is equal to minus 1 over s into e raised power minus infinity is simply 0. That's 1 over infinity. And this is minus e raised power minus sa or as. So if I rewrite this now, I mean, this is just minus 1 over s into minus e raised power minus as. So finally, we see that the Laplace of the shifted unit function u of t minus a is simply 1 over s e raised power minus as. So, and with that in place, this is what we get for the shifted step function. Of course, this is only guaranteed for s greater than 0. Okay, for s greater than 0. So that goes. So let's have an example to drive home the point. So the question is, here we have this example now. Find the Laplace transform of the function f of t equals t minus 2 into u into t minus 2, where u of t minus 2 is the shifted unit step function. This function represents a signal that starts at t equals 2 and behaves as t minus 2 for t greater than or equal to 2. Okay, so to take care of that, in step 1, we have to define the function. Of course, we've been given the function itself, so we just clearly identify it. So the function f of t, which is equal to t minus 2 into u of t minus 2, is defined as the shifted step function f of t equals 0 when t is less than 2 and t minus 2 when t is greater than or equal to 2. That's what we have. So, and this happens such that for t greater than or equal to 2, f of t is equal to t minus 2. And for t less than 2, we have f of t to be equal to 0. So with that done, we can move on to step 2. So in step 2 now, so we use the shifting property, of the Laplace transform. So that's one of the properties we had seen, I think, in the second video, in this playlist on Laplace transform. So use the shifting property. So we know that the Laplace transform of t minus a into u of t minus a is a well-known result. It's a well-known result. And that is that the Laplace of t minus a into u into t minus a is the same thing as e raised to minus as all over s squared. All over s squared. And that happens for s greater than 0. Okay, so in this case, a is equal to 2. All right, so the Laplace transform, or the Laplace transform of t minus 2, u of t minus 2 is the Laplace of t minus 2 u t minus 2, and that is equal to e raised to minus 2s all over s squared for s greater than 0. With that done, we can actually then yeah, I mean that's all we need to do. Basically, there's no point dragging it further. So we can just finalize, right? So yeah, that's the final answer. So we can just say this now. Therefore, the Laplace transform of f of t equals t minus 2 u into t minus 2 is the Laplace of f of ft, which is the same thing as e raised to minus 2s all over s squared for s greater than 0, and that is what we have. So with that in place, let's quickly take okay, well, there's no point. I can just talk about that. So the unit function u of t is used to represent systems that turn on or turn off at a specific time, and its Laplace transform is simply 1 over s. As for the shifted unit step function u of t minus a, that the shift that shifts the activation to t equals a, and its Laplace transform is e raised to minus as all over s. So these transforms these transforms are essential for analyzing piecewise functions, especially in control systems and signal processing. By using the shift property, we can transform functions that involve delays or changes. Okay, let me write this last line as the conclusion, right? So by using the shifting property, we can transform functions that involve delays or changes in behavior at specific times. Okay, so can we take some practice questions to see how well this is understood? Compute the Laplace transform of the function f of t equals e raised to power 3t multiplied by u into t minus 1. Okay, that's the first. Number 2, find the Laplace transform of the function f of t equals t plus 3 u into t plus 3. Then number 3, find the Laplace transform of the following. So A, f of t is t squared plus 4t, u of t minus 2. B, f of t is sine 2t, u of t minus 1. Um, C is f of t equals t minus 4 raised to power 3, u into t minus 4. Then D, we have D is f of t is e raised to power minus 2t, e raised to power minus 2t, t minus 3, u into t minus 3. You may want to consider convolution for some of them. Then we have f of t again, which is 2t, u of t minus 5. And I think lastly, we have f of t equals cos t, u of t minus 1. So you may want to let me have the answers in the comment section, either on YouTube or on Facebook. And of course, in the comments also, let me know how helpful these videos are for you. And if there's a topic you'd like me to teach or a problem you'd like me to solve, And for those who have subscribed to this channel, thank you so much for that. And if you have not subscribed, you want to do that right away because there's a lot for you to learn on this channel. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing maths right. Bye.